Okay. Yeah, so let's welcome Jaehak Lee from KIST, Korea. He is going to talk about fault-tolerant quantum computation by hybrid qubits with bosonic cat code and single photons. So I believe this work was published recently in PRX Quantum, and Jaehak Lee is a scientist at KIST, and there are other papers also in the list, including Liang Jiang and Song Wu. So like it's my privilege to have Jaehak here. And Jaehak, the stage is all yours. Like, please start, your talk. Yeah.
Uh, Thank you for introducing me. Also, thank you for the having this nice opportunity to introduce my recent work. In this work, I study about some hybrid approach in quantum error correction. The hybrid approach means that we use a continuous variable and a discrete variable together. So for the continuous variable, we adapt the cat code, and the discrete variable, we employ some single photon qubits. And this work is done by many collaborators, and Nuri and Sungwoo is the uh, collaborator in KISS, and so Sakyung is the now in Sydney, and Hyunsuk Jung is the professor in SNU, and Liang Jiang is very famous guy in Chicago University. So in this talk, I'll start with some in encoding method of qubits in Bosonic mode. Typically, there are two separate approaches. One is using the discrete variables, and another one is using the continuous variables. And then we have some another important encoding method, that is the bosonic error correction code. That is, we can encode a qubit into a bosonic mode so that qubit can be errors in the qubit can be corrected in a single bosonic mode. And using this encoding method, we devise a new approach using a hybrid qubit. So in this hybrid qubit, we use the discrete variables and continuous variables together, also with some bosonic error correction code. And after defining hybrid qubits, we also define the hybrid fusion gate, which will be the basic building block of our scheme. And then using these hybrid qubits and hybrid fusion gate, we simulate the fault tolerance of our method. And I will also talk about some physical realization of this hybrid method. So I think most of you are very famous with this, very familiar with this. So qubit, what is qubit? So qubit is just a quantum bit. It means that the bit is info bit means the basic unit of the information encoding as a 0 or 1. But in the qubit, we in the quantum mechanics, as the quantum mechanics allow the superposition, so in the qubit, we can represent the superposition of 0 and 1. So this qubit can be realized in many physical systems, which can be done by uh, setting two discrete levels. So many development has been done in superconducting system and trapped ion, diamond epicenter, and some optical systems. And in some, uh, so encoding a qubit, we need two levels. But if we have more levels, we can encode a qubit in many different ways. So in the bosonic system, we have a infinite energy level, represented as a harmonic oscillator. So the Hamiltonian of the harmonic oscillator, we can describe this in two ways. One is the using XMP, position and momentum, so it becomes x squared plus p squared, or we can represent it as with the photon number uh, operator. So using this number operator n, we can use the discrete variables. If we use the x and p, we can use the continuous variable. So we have some very different approaches in encoding a qubit into the harmonic oscillator. So in the discrete variable approach, we can encode a qubit using a single photon. The most famous way is the dual layer encoding. So if we have a photon in the upper path, we represent 0. If we have the photon in the lower path, we represent 1. And also we can use the polarization of the photon. So actually these two are equivalent because we can uh, make the polarization photon into a different into different path using the polarizing beam splitter. So using the single photon encoding of the single photon encoding, we can implement a single qubit gate very efficiently using the linear optical element. So we can make the Hadamard gate with some wave plate, and any arbitrary rotation can be done also with combination of the wave plates. But the problem is that the photons do not interact easily. So it is very hard to make some two qubit gates. So we can only make two qubit gates in a non-deterministic way. So in this scheme, we present some single ancillary single photons, and then we make some interaction with using the linear optics, beam splitter or and phase shifter, and then we post-select the result in the ancillary mode, post-select the single photon detection in ancillary mode. So after successful detection, we have some controlled Z gate here, but if the detection result is not what we want, then this two qubit gate fails. So we can only implement the two qubit gates in a non-deterministic way in this DV DV encoding of the single qubit, DV encoding of the qubit. And then another approach is to use the continuous variable. So in this continuous variable approach, we can encode a qubit into a coherent state. So 0 can be represented with a coherent state with plus phase, and 1 is encoded in a coherent state with different phase. Here the we set minus alpha. Uh, these two coherent states are very classical optical state, but in the qubit, we should also represent the superposition of 0 and 1. Then the plus state becomes the even superposition of the plus alpha and minus alpha, and minus state becomes the odd superposition of the plus alpha and minus alpha. So we need some nonlinearity to implemented this current state qubit. So because we have some non-linear superposition of the current state, so actually it is a little bit hard to implement some single qubit rotation. But in this scheme, we can make Bell measurement very efficiently. It can be done by using some only single beam splitters and two parity detectors. So we using we get if we get some detection result here, then we can discriminate for the best states. And in some case, we have some failure probability, but this failure probability becomes extremely small when the amplitude alpha becomes large. That is because the failure occurs when we have we detect the vacuum on both output port. So if the amplitude of the current state becomes large, the this vacuum detection has small probability, so it is suppressed in exponentially. And next, I move on to the quantum error correction. So, I think most of you are very familiar with this. So I will just move quickly. So quantum error correction is a method to protect qubits from environmental noise. So if we want to protect a qubit, we need a larger space for the logical qubit because if you have only two levels, we cannot correct the error. So we need much larger space to encode a qubit. So we use many number of qubits to encode a single logical qubit. So um, popular error correction code is given here. One is the 7-qubit string code, and the next one is the two-dimensional lattice surface code. And another the last one is the QEdit piece code, which can encode a logical qubit in very efficient way. But I'm not going into details about this error correction code, but I want to talk about the Bosonic error correction code. Uh, in the previous slide, I said that we need many physical qubits to encode a single logical qubit. But in this Bosonic mode, we can make error correction only in a single Bosonic mode. That is because single Bosonic mode has infinite level structure. So there are many different ways of encoding a qubit into a harmonic oscillator. One famous one is the GKP code developed by Gottesman, Kita, Preskill more than 20 years ago. But this code has drawn many attention these days. That is because people realize that the quantum error correction is really important. So in this GKP code, we encode a qubit into a grid in the phase space. So we can see some points in the phase space like this. And actually this can be represented as a superposition of the squeeze state in the wave function. So the point is that the information should be encoded in this grid point, lattice point. If the lattice point is out of the encoded information becomes out of this lattice point, we can bring it back to the lattice point to restore the information. So this is the error correction scheme originally developed by these guys. So to perform the error correction, we need an ancilla GKP state, and we do some controlled sum operation, and then measure the quadrature. So and then we can get the displacement from the lattice point. So if we displace it back into the lattice point, we can correct this displacement error. And another Bosonic code is a cat code. In this cat code, we used coherent superposition of the coherent state. But here we use only even superposition of the coherent state. So zero state is represented as alpha plus minus alpha, and 1 is represented as I alpha plus minus I alpha. So we used four different coherent state and even superposition of them. Also, other states can be represented as some even superposition of this four coherent state, and we are using the even superposition so that this logical qubit reside in the even number space. So if a photon loss occurs, the even photon number state becomes the odd photon state. So the parity changes, and then if we measure a parity measurement, that uh, informs us that if there has been a photon loss or not. So the parity measurement works essentially works as a syndrome measurement. But actually, to perform the error correction, it is very hard to measure parity only, not disturbing the encoded information in this logical qubit. But we have some scheme we'll explain later. So this is our main idea of the hybrid quantum computation. This work is published in PRX Quantum recently. So in this hybrid approach, we define a hybrid qubit. In this hybrid qubit, we use polarization qubit and K-code qubit together to define this logical qubit. So for the logical zero state, the polarization is the plus polarization. That is in this plus 45-degree direction. And then the cat code is given in the according to the superposition of the alpha and minus alpha. And for the logical one state, the polarization becomes minus 45 degree. And then the cat code becomes the superposition of I alpha and minus I alpha.
By the way, Jack, so so here, like, do you have constraints on, as you had in the last slide, right? So you wanted even number cat codes, right? I mean, can you go to the previous slide?
Yes, the
Yeah. So
logical
basically,
basis is given in even
exact.
number.
Yeah, yeah. So even cat, like you have an even cat states, right? So that's the
Right.
only, you keep the same constraint, like even in your encoding, but just
Yes.
that have this extra degree of freedom where in the polarization you are, like, which you are bringing from the polarization, right?
Actually,
And that's the.
that means this means that the head code photons uh, actually for this polarization qubit we have ancillary photon, not photons for the head code. The ancillary single photon has polarization given in plus or minus.
Uh-huh.
So we need two modes. One is for the polarization and another one is for the head code.
And but in general, I mean, yeah, I mean, why I'm asking this, because this recently we had a talk on something called spherical codes, you know,
Mm.
and so there is this formalism of spherical code, which has, which generalizes all of these cat codes and GKP codes and so on. And basically, you are thinking about, even cat codes, and with this,
Yeah.
with this extra degree of freedom, which is in the polarization. I
Yeah.
was thinking, I mean, maybe one can think of even more general, like a hybrid qubit,
Yeah.
where, your C alpha plus basically comes from spherical code, and
Yeah.
C alpha plus and Ci alpha plus, and then, use this extra qubit for, like this, the polarization qubit basically. So it's kind of a hybrid qubit, but not with cat code, but, but with spherical codes. I mean, very, just passing remark maybe. Yeah.
Yeah. So I think that there are many various ways of the define the hybrid qubit, but in this work we use some simplest one using the polarization
Yeah.
and encode. Yeah.
Yeah, yeah. No, I mean, I see that the only constraint you need to be, like this even cat codes. But
Yeah,
as
that's
I'm
right.
saying that for the larger family of codes where you can carry on this constraint, and maybe I don't know, what parameters you get and all. Maybe those parameters could be improved by taking some of the best bosonic codes with, the same constraint that you have here, and having this extra degree of freedom in the polarization qubit.
Yeah, that's right.
Yeah.
Okay. So using hybrid qubit, we have many advantages. The first one is that we can use the photon loss correction of the K code into this hybrid qubit. And I said that for the K code, the implement single qubit notation is very hard to implement, but using some ancillary polarization qubit, we can implement the single qubit notation very efficiently. And another one is that we can do hybrid fusion operation very efficiently. The hybrid fusion operation means the kind of Bell measurement. So in the previous slide, I introduced the Bell measurement of the cat code, so it can be done very efficiently. For the hybrid qubit, we can also do efficient Bell measurement, and it is even more efficient than a single cat code qubit. So uh, let's first explain about the single qubit rotation. So we use this set of the universal gate. So for the single qubit rotation, we need to implement a Pauli X gate and arbitrary rotation along Z axis. So they can be done by simply done by some wave plate and the phase shifters. Also, we can do any arbitrary rotation along z-axis using three wave plates. But for two other gates, Hadamard and Control Z, um, actually it's somewhat hard to implement in using linear optics. So we employ the gate teleportation. So for the gate teleportation, we prepare some resource state, entangled state, and do the Baire measurement and get the output state. So this Baire measurement we call hybrid fusion operation. In this hybrid fusion operation, we do Baire measurement on DV qubit and CV qubit separately. So here uh, for the DV Baire measurement, we employ typical type 2 fusion gate. And for the cat code Baire measurement, we employ this scheme. Actually, this scheme is developed by this Anderson's group recently, published it in Physical Review Research. And actually, there are another similar scheme developed by Daikinsu and Ralph, published in the PRA. These two papers have been published in very similar days. But we also tested this scheme and this scheme, but we find that we get higher performance using the Anderson's group scheme. So in this scheme, the scheme is the same as the Bell measurement in current state qubit. But here for the cat code qubit, we need one beam splitters and photon number resolving detectors. And in this photon number resolving detectors, we use the modulo 4 numbers. So if we get some measurement patterns, vacuum or not, and also we analyze the photon number detected, we make the decision of the best state. And we have some small probability of error because two cat the logical basis of the cat code is not perfectly orthogonal, but the probability is exponentially small. And the one important thing is that we use cat code encoded in the even photon number space. So total photons detected in these two detectors should be even. But if a single photon has been lost somewhere in this scheme, we can also we should detect even odd photon numbers. But even in this case, we can uh, decide the Bell state, and the error probability is also very small. So we can do efficient Bell measurement even in the case of the single photon loss. But if we have more than two photon loss, then actually there has been some logical errors. But two photon loss has a much smaller probability than the single photon loss. So correcting a single photon loss error is sufficiently good. So we define this hybrid fusion gate. and we analyze the error rates in the hybrid fusion operation. So you can see that x error becomes smaller and becomes larger as the current amplitude alpha becomes smaller. It means that if we increase the encoding amplitude alpha enough, then we can make the x error rate becomes if exponentially small. You can see like this. So if we have if we increase alpha, then logical x error becomes extremely small. But on the other hand, if we increase alpha, the z error rate becomes large. That is because the large cascade is is fragile against the photon loss. So we in this hybrid qubit we have some property of the bias noise, but actually we in this work, at least in this code, we do not use the bias property. But so we anyway we should correct the remaining error in after this operation. So the next step is to concatenate our hybrid qubit into some other autocode. So for the autocode, we
So basically, like Jack, you are saying that like against photon loss, you don't have like much tolerance because the original cat code cube code they are not so good against for photon loss, right? And I think
have that means that if we have large cascade, the management becomes much efficient, but it becomes fragile against the photon loss. So it is important that we need to choose the uh, optimal value of the
oh, shall I
alpha.
take some? I see.
Yeah.
Yeah.
So here to make the quantum computing fault tolerance, we employ the RH lattice as an autocode of our scheme. So in this autocode, we implement the surface code in measurement-based quantum computing. So we to implement the RH lattice, we need a very large cluster state like this. So to construct this RH lattice, we start from the 3-qubit GHZ state, 3-qubit cluster state. So we prepare three 3-qubit cluster state and make some hybrid fusion operation. So they are consumed. These 2 qubits are consumed during the hybrid qubit, and also these 2 qubits are consumed. Then we have a 5 qubit left, all entangled in this graph structure. And we used many of these 5-qubit star type 5-qubit cluster state like this. Uh, and then we pile this five star 5-qubit star type cluster state like this. Then we again perform hybrid fusion operation to make edges between this and this. So after all hybrid fusion gate, we can get this RH type of cluster state. And during this hybrid fusion operation, we have some error rate. So we assign the error rate into this all of these data qubits, and then we make some decoding using the minimally perfect matching algorithm. So after decoding, we count the number of uncorrectable errors, and then it becomes the logical error. So from this simulation, we calculate the loss threshold of our scheme. So here is our result, and this one is previous some result from the previous work. For this work, we use the hybrid qubits using polarization qubits and the K-code. And for the previous work, we used the polarization qubit and the current state qubit. So in this hybrid qubit, we do not implement the photon loss correction because we use only two components of the current state. It is not encoded in some even photon number. So we use the K-code photon loss correction in this hybrid qubit. So we find that the photon loss threshold becomes large, 4 times larger than previous one. We also make some comparison with not only with the RH lattice, also with the thin code, but we find that thin code is not that efficient. So we have high threshold in using this hybrid cat code and the RH lattice. And actually, this threshold, as far as we know, this threshold is the best threshold in CV or hybrid approach in optical quantum computing. And next, we also compare the resource overhead in our computing architecture. And first, we compare our hybrid cat scheme with the previous hybrid current scheme. And for the fair comparison, we count the we assume the same unit resource. That is the hybrid coherent pair is becomes the unit resource, and for the hybrid cat state, we assume uh, a hybrid cat pair can be generated using 8 pairs of the hybrid coherent pairs. We will explain this later, but even we have more resource to generate hybrid cat pairs. It is shown that we need smaller number of the unit resource to achieve the fault tolerance. And we also compare with the other schemes in optical quantum computing. Actually, most of them are DV quantum computing. So actually, saying comparison is not easy because we have some different kind of the encoding method and different kind of the resource state. But uh, we tried, we have tried to make a very fair comparison. So we set some similar level of the difficulties in make resource state. So we show that as a result, we show that our scheme is much more efficient than other schemes, and it by one order of magnitude. So we show that our hybrid scheme has a higher loss threshold and much lower resource resource overhead. And last, I'll talk about some physical implementation of our hybrid qubit. In optical systems, actually has been some demonstration of the hybrid qubit. Uh, that is the scheme is given like this. We have some DV mode and CV mode, and we apply some photon addition or photon subtraction operation on the CV mode, and then we detect some single photon combined with DV and CV mode. So this this beam splitter erases the photon phase space information. So unless this DV mode and CV mode get entangled. This is the same in this scheme, and this experiment has done in Julian Laura's group in France. So, but in this scheme, only hybrid coherent state has been generated from this scheme. So we need to extend the hybrid coherent scheme into the hybrid cat qubit. So this is the scheme. So we prepare two pairs of the hybrid coherent pairs, and then mix them using some type 1 fusion gate for the DV1, and for the CV qubits, we mixed by pin splitters. So by post-selecting even photon number here, we get a 4-component CAD code here. So from the current state qubit, we get a CAD code qubit in CV mode. Actually, this scheme has been proposed by the Hestrup and Andersen in Denmark. So uh, we start with two hybrid current pairs, and the success probability of this DV fusion is 1/2, and the success probability of this CV fusion scheme is 1/2. So we assume that one hybrid cat pair is as expensive as 8 hybrid current pairs. This is quite a fair assumption. So here we show how we can implement hybrid qubits in optical systems, but also we can do hybrid approach in other systems, something like a superconductor or an ion trap system. So actually, there has been many experiments to demonstrate the Bosonic code in these systems. So the 4-component CAD code has been demonstrated in uh, a superconducting system, and also GKB code has been demonstrated in superconducting and ion trap system. And also, we can implement efficient DV and CV nonlinear interaction in superconducting and ion trap system. So this is the experiment by Kiwan Kim's group using the ion trap system. So we used the level structure of the ions for the DV mode, and the phonon mode, we employ phonon mode as CV mode. So they can make any arbitrary controlled beam split rotations between DV and CV mode. And here for the here in the uh, this experiment has been done in Yale group. So here for the DV mode, they used some transmon, and for the CV mode, they employed the microwave cavity. So controlled rotation gate has been demonstrated here. So actually, this kind of DV-CV nonlinear interaction is not easy to implement in optical system, but it is much easier in this kind of system. So we expect that DV-CV hybrid approach can be available in various platforms, not only in the photonic system or any superconducting system, ion trap system, and many various systems. So this is all. So in this work, we suggest the hybrid approach in quantum computation using single photon qubit and K-code qubit. And we define hybrid fusion operation, conducting Bell measurement, as well as the photon loss detection. So we do the simulation using RH concatenated with RH lattice. Then we find the improvement in loss threshold and the resource overhead. And we think about we can extend this hybrid approach in many different ways. So for example, we can use the error bias properties so that we can we can employ some different kind of outcode which is specialized for the error bias qubit. And also we can do some hybrid approach using different kind of Bosonic code such as QKP code and binomial code also. Uh, this is all of my talk, and thank you for your attention.
Yeah, thanks, Jack. Basically, I was, thinking about this one, like hybrid approach with, let's say, spherical codes, like, so, yeah, I think maybe, uh, yeah, like, I mean, whether that will make sense. Okay, so, I mean, it was a very nice talk. If people have questions, maybe just unmute yourself and ask. If any question anyone has. Okay, seems not. Okay, so in that case, I will thank. Maybe Andrew, you have a question?
Yeah, just real quick clarification. So in your in the overhead analysis, I'm just wondering, so the overhead analysis that you did is on the number of this hybrid qubits. Is that correct? Or?
Yeah, we actually we count the number of the hybrid current state pairs. So in
Okay.
our simulation using a hybrid cat cat qubit, so we count this single hybrid cat pair is the same as the 8 hybrid current pairs. So we count the number of these hybrid current pairs. That is because we need to make a fair comparison between hybrid cat scheme and hybrid current scheme.
Okay. So yeah, I'm just wondering, so what about the overhead for the time complexity of your fault tolerant computation? Is that like, I don't know, like I'm
Yeah,
just wondering.
yeah, that's a very good question. So for the construction of the hybrid RH lattice, we described in 2 steps. So actually, every hybrid fusion operation in the first step can be done simultaneously. And also, any hybrid fusion gate in step 2 can be done simultaneously. So we only need 2 steps to uh, construct this RH lattice.
Ah,
Yeah, but
okay.
actually, uh, in the realization, the actually this is the time axis. So we generate a single layer. We generate the RH lattice by layer single layers. So for the single layers, we say that we can do in to generate the single layer in 2 steps.
Okay. Oh, okay. So I see. So wait. So how do we implement the gate here? Sorry, I think I might have missed that.
I mean, this hybrid fusion gate. For the hybrid
Oh,
fusion gate, only do the bare measurement.
I see.
Yeah.
Right.
Actually, we need some. Actually, we need the unit resource, this 3-qubit entangled state resource, but we have some method to generate this in our paper, but we assume that this is the Beijing resource we can make. And if we start with this Beijing resource, we need only 2 steps of for this large cluster state.
Right. Okay. I see. Thanks.
Yeah.
Any more question? If not, let's just thank Jack. Very nice talk, Jack. Do you mind sharing the slides? I will share with people in the Discord channel. I think you are in the Discord channel, right? So can you just add there is a channel called Asia Pacific, something like, talks.
Yeah, yeah,
Yeah,
I know that. Yeah,
and you just add there your slides. Huh?
yeah. Okay, I upload my slide there.
Thanks a lot. So
Yeah.
let's just thanks Jack once more, and see you everyone. Probably like next month we will have 2 talks only,
Mhm.
and then after that we will have a break. No quantum error correction, so everyone will be happy. And in January we will start with like so we have 2 talks next month, and after that like some break, and then in January we start again. Okay, so thanks a lot, everyone. Yeah, thanks for coming. Yeah.
Okay, thank you.
See ya.